Detectives, today we have a mystery to solve. Our mission: to uncover how the nearest neighbor regressor or KNN regressor works. But this isn't just a simple case, oh no. We'll be diving deep into some tricky territories, like how does KNN predict numbers, what are KD trees and ball trees, and why do we use them? What happens when we work with high-dimensional data? And most importantly, how do we escape the curse of dimensionality? Spoiler alert, it's not magic, but it feels like it. By the end of this mission, you'll be an expert in KNN regression, knowing how to use it and when to avoid it. Alright, detectives, imagine we have a crime scene. But instead of fingerprints and footprints, we have data points. Each data point is a circle, and its size is what we want to predict. But we don't know the size of a new circle that just appeared. How do we decide what size to give our new circle? Do we just take a wild guess, or do we rely on our nearest neighbors for help? Luckily, we have two clues, feature 1 F1 and feature 2 F2. These two features tell us about our circles, and by looking at past cases or training data, we can figure out the missing size. Here's our investigation plan. We check every point in our training data. We measure the distance between our test circle and each of them. We find the closest one. And finally, we assign the same size to our test circle as its nearest neighbor. Simple but powerful. The closer the neighbor, the more likely they have similar sizes.
But wait. What if there are multiple neighbors nearby? Should we just trust the closest one, or do we need a second opinion?
Good questions. This is what I call the problem with k equals 1, the lone witness. Let's say we only ask one neighbor about the missing size. Sounds like a simple plan, right? But there's a catch. What if our nearest neighbor is unreliable? Maybe they're an outlier, completely different from the rest of the data. If we trust just one point, we risk making a wrong prediction. To fix this, we don't rely on just one point. Instead, we increase k, the number of neighbors we ask for help. Let's run a few scenarios. For k equals 2, we take the average of 2 nearest neighbors. For k equals 3, we take the average of 3 nearest neighbors. And so on. This way, we smooth out errors and get a better prediction. If we have k nearest neighbors, our predicted value, let's call it y cap, is simply the average of their sizes. Here, y represents the sizes of the k nearest circles we found. This means our prediction is more stable, less sensitive to noise, and way smarter. But now, we have another mystery. What is the best value for k? Too small, and we risk errors. Too big, and we might lose important details. How do we find the perfect k? If you know the answer, comment down below to let everyone know. Alright, detectives, we increased k to 4. Great. Now our test circle is listening to 4 neighbors instead of just one. But a new problem appears. One of the closest neighbors whispers,
"Hey, why are you listening to that guy Y over there? He's so far from you."
Our test circle replies,
"Well, I need to check with 4 neighbors, and he's my 4th closest."
Another neighbor interrupts,
"Yeah, but he has the same influence on you as we do. That's not fair. We are way closer."
Our test circle now has a dilemma. How do we make sure closer neighbors have more influence than those who are farther away? Simple. We give more weight to closer neighbors and less weight to farther ones when averaging their values. Mathematically, this means instead of just taking the simple average, we multiply each neighbor's size by a weight based on their distance. A common choice is using 1 divided by the distance, meaning closer neighbors have a bigger say. This is called weighted KNN, and it makes our predictions much more reliable. Alright, detectives, let's step into the domain of simple math and see the impact of weighted KNN ourselves. We're using k equals 4, and have the following neighbors. In standard KNN, we don't consider distance, we just take the average of the sizes of the 4 neighbors. Hence, in this case, we predict the size of the test circle y hat as 151.99 plus 179.71 plus 126.04 plus 91.23, divided by the total number of neighbors, 4, which would give us 548.97 divided by 4, which is 137.24 approximately. So, our test circle gets a predicted size of 137.24. But wait. Is this the best prediction? Look at neighbor 4. It's far away, yet it influences the result just as much as neighbor 1. That's not fair, right? Let's fix this by using weighted KNN. In weighted KNN, closer neighbors have a stronger impact. A common way to assign weights is using 1 divided by the distance. Hence, we can easily calculate the weights we need to assign to each of the neighbors based on how far they're from our test circle. Now, let's apply these weights to our prediction formula. Y hat equals 0.2857 multiplied by 151.99 plus 0.1901 multiplied by 179.71 plus 0.1173 multiplied by 126.04 plus 0.0790 multiplied by 91.23 divided by the sum of weights, that is 0.2857 plus 0.1901 plus 0.1173 plus 0.0790. Upon solving this hideous-looking equation, we get y hat equals 148.19 approximately. In normal KNN, our prediction was 137.24, but with weighted KNN, it adjusted to 148.19, giving more importance to closer neighbors. This proves that weighted KNN is smarter. It avoids letting faraway points influence predictions unfairly. So, detectives, what would happen if we picked a huge K value, like 100? Would our test circle be listening to way too many opinions? We'll get to the answers of these at the end of the video. For now, keep these in your mind to wonder. Detectives, we've solved some small cases. But what happens when the crime scene is huge? We started by looking at a few neighbors to predict values, but what if we have millions of data points? Do we still check every single one? That would be like a detective knocking on every door in an entire city, exhausting and slow. In a naive approach, the algorithm, first, calculates the distance between the test point and every single training point. Second, sorts all distances to find the K nearest ones. And third, averages their target values to predict the result. Sounds reasonable, right? But here's the issue. Though training time is O1, practically nothing since no training happens, KNN just stores data. So, that's a win, but prediction time would be O and D. Within training points and D features, this slows down as data grows. So, what happens when N is a million? If you had a million data points and a test query, you'd be calculating a million distances. That's painfully slow. We need to optimize our detective work. Instead of blindly searching, we can structure our dataset smartly so that we check only relevant data points. And that's where KD trees and ball trees step in. Alright detectives, we need to organize our data so we don't have to search every single point. Let's build a KD tree, but first, we have an important question. Which feature should we split on first? We could split the dataset randomly, but that's not smart. Instead, we look at the spread of each feature. Spread means how much the values of a feature vary and the feature with the highest spread is chosen first.
But wait, what if all features have roughly the same spread?
Great question. In that case, we just pick one randomly. In our case, the spreads are similar, so we randomly choose feature F1 to split the dataset first. Now that we have chosen feature F1, how do we split? Simple. KD tree picks the median value of F1 and splits the dataset into two halves. One half goes to the left, and the other half goes to the right. Boom, just like that, our dataset is divided, making our search process way more efficient. Alright detectives, our KD tree is ready, and now it's time for action. Our test data point arrives, and the algorithm starts searching for its nearest neighbor. But how does it know where to go? The first thing our test point does is check the root node. Since we split based on feature F1, we compare our test point's F1 value with the root's F1 value. Since our test point has F1 equals 22, and the root node was split at F1 equals 14.13, what happens? Since 22 is greater than 14.13, the test point says, I belong in the right half, and moves right and completely ignores the left leaf. Now, instead of checking every single point like in the brute force approach, the algorithm only looks at the points in this right leaf. It calculates distances only for those points, almost having the number of calculations. This is why KD trees are so powerful. Instead of searching through a messy pile of data, we quickly zoom into the right neighborhood and search only where it matters. Alright, detectives, we've been using the KD tree to speed up our nearest neighbor search, but a new challenge has emerged. What if our test point is lurking near a boundary? Based on the value of feature F1, it'll again search in the right leaf and selects the data point closest to it. Would the selected neighbor truly be the closest one? Or have we overlooked an even better suspect on the other side? Time for the KD tree to double-check its work. Every time we reach a potential nearest neighbor, the KD tree detective doesn't stop just yet. It asks, what's the distance from the test point to the boundary wall? Now, here's the key. If this boundary distance is smaller than the distance to our current nearest neighbor, we might have a problem. Why? Think just for 5 seconds here. Because this means there's a chance an even better neighbor is just across the boundary. When this happens, the KD tree detective doesn't just stand there, it takes action. It jumps the boundary and starts looking in the other half of the tree, checking the distances of those points as well. This way, the algorithm makes sure we don't miss an important suspect hiding just beyond the split. Alright, we've jumped the boundary and checked if there was a closer suspect on the other side. But wait, there's one last thing to investigate, the split node itself. The point that was chosen to divide the dataset, it doesn't belong to any leaf. Could it be the closest neighbor? Remember, when we built the KD tree, we split the dataset at specific points. These are called split nodes. These points are not assigned to either of the two regions directly. Instead, they serve as the dividing line. So, before making our final decision, the KD tree detective stops and measures the distance from the test point to this split node. Why? Because it could still turn out to be the closest neighbor. Imagine standing exactly at the boundary of two zones. Even if there were closer neighbors inside a leaf, the boundary itself might be the true nearest point. And that's it. The KD tree detective doesn't just stop at the first good answer, it double-checks across boundaries and even verifies the split node itself before making the final call. But hold on, detectives. We started using KD tree to avoid brute force, but in this case, we ended up checking almost every point again. This feels like we're back to square one. Is there any smarter way out? We've seen how boundary cases force KD tree to check extra distances. Let's see if we can make KD tree more efficient by increasing its depth. So far, we've only split the data once, using feature F1 at the root. That means each region is still quite large, making it harder to eliminate unnecessary points. But what if we split again? This time, we pick feature F2 to further refine our search. KD tree follows a cyclic selection rule. First, it chooses F1, then F2, then back to F1, and so on. This ensures we're systematically dividing the space. At each level, the median value of the selected feature is used to split the dataset, just like before. Now that we've split the data again using F2, the test point falls into an even smaller region. This means that instead of checking half the dataset, we've narrowed it down even further. The deeper the tree, the fewer points we need to consider. Alright detectives, let's put our deeper KD tree to the test. Will increasing the depth really save us from extra calculations? Or are we still stuck checking too many distances? Let's investigate. We start by checking the test point's distance to all the points inside its assigned leaf. This is our first estimate of the nearest neighbor. Now, we calculate the distance of our test point to the nearest boundary at depth 2, the one that was created when we split using feature F2. If this boundary is closer than our nearest neighbor so far, we must check the neighboring leaf. In our case, boundary is closer to the nearest neighbor so far, so we need to check at the neighboring leaf. After traversing to the neighboring leaf, we calculate the distance to the new data points found there. Once done, we step back up and check the test point's distance to the split node itself. So far, the nearest neighbor is still the one we found at the first leaf, but KD tree does check everything to be sure. Let's see if there is still the requirement to check all the data points. Now we move up again, reaching the original split at the root node feature F1. We measure the test point's distance to this boundary. If the boundary is closer than our nearest neighbor so far, we must investigate the opposite branch, and upon investigating, it's clear we do need to go to the other side. But which side of the leaf to check first in this side of the tree? Since our test point has breached the root boundary, we check the right side first based on our test point's F2 coordinate. We now decide whether to continue by measuring the distance to the next boundary. If the distance to the next boundary is greater than our nearest neighbor so far, we can stop searching that branch. This is how KD tree eliminates unnecessary calculations by pruning entire sections of the tree. Finally, since we breached the root boundary, we do a last check, the distance to the root node itself. And with that, we've gone through all necessary checks, without scanning every single data point like brute force. So, what did we learn? Even with all these extra checks, our deeper KD tree still saved us from checking some of the dataset, a huge improvement over brute force. This is the true power of KD tree. It doesn't just find neighbors, it smartly avoids wasting time on unnecessary calculations. Now, let's talk about a big problem in machine learning, the curse of dimensionality. It's one of those sneaky villains that makes our nearest neighbor search slow and inefficient. But don't worry, we have a new hero. Ball tree. Let's break it down. Imagine you're searching for your lost detective notebook in a small room. Pretty easy, right? But what if the room had 100 floors and each floor was the size of a stadium? Now, searching for that notebook is much harder. This is what happens when dimensions features increase in our dataset. In low dimensions, data points are close together, and finding the nearest neighbor is easy. But in high dimensions, data points get far apart, and distances become less meaningful. We learned that KD trees split data based on feature values, but in high dimensions, this method becomes ineffective because too many dimensions to split on. The tree grows deep but doesn't separate points well. Pruning becomes useless. Boundaries don't help much in high dimensions, so we still end up checking most points. Traversing back is costly. The algorithm wastes time searching extra branches. To tackle this high-dimensional chaos, we need a better structure. Ball tree, instead of splitting along feature axes like KD tree. Ball tree groups data into nested balls hyperspheres. Let's understand them and make one ourselves. But before going into all that, let me ask you one thing for you to wonder. Can we use dimensionality reduction techniques and then use KD tree? Think on it. We will discuss the answers of these at the end of this video. Now, coming back to ball tree, in order to construct one, first, we compute the mean of all data points. This gives us a central reference for our dataset. Next, we calculate the distance of every point from this center. The farthest distance is chosen as the radius of the sphere. This ensures that all points are inside the circle or ball in higher dimensions. Each node stores the center of the ball, that is, the mean of points in that node, the radius farthest distance from the center. Pointers to left and right child nodes dividing the ball into smaller balls. Now, moving to the depth of 1, let's see how ball tree stores information in the leaves. Unlike KD trees, which rely on predefined features, ball trees take a unique approach to determine how to split the data. Let's break it down step by step. Instead of splitting along a feature axis, ball tree finds an optimal direction for the split. Here's how. First, pick a random point from the dataset. Second, calculate distances from this point to all other points. Select the farthest point, let's call it A. Now, take A and repeat the process and find the farthest point from A, let's call it B. These 2 points A and B are likely to be at opposite ends of the dataset. Now that we've found 2 farthest points, A and B, let's see how the ball tree actually splits the dataset to build its structure. We treat A and B as the 2 extreme points of a new axis. Every other data point in the dataset is projected onto this line, just like casting shadows onto a straight path. Once all points are projected, we calculate the mean projection value along this line. This mean point is chosen as the splitting boundary. This ensures that the 2 groups have almost equal numbers of points, making the tree balanced and efficient. Now that we've split the dataset into 2 groups, it's time to enclose each of these groups inside new spheres, just like we did before at the root level. For each group left and right from the split, we compute the mean of all points. This becomes the center of the new sphere. Then, calculate the distance of all points from this mean. The farthest distance is chosen as the radius of the sphere. This ensures all points within that group are enclosed inside the sphere. Now that the ball tree is built, let's see how it searches for the nearest neighbor when a new test point arrives. The test point arrives, and we need to find which leaf node it belongs to. Ball tree calculates the distance from the test point to the center of each child node sphere center. The leaf node with the closest center is selected for further exploration. Once the test point reaches the assigned leaf, the ball tree calculates its distance from all data points inside that leaf. It selects the closest data point as the nearest neighbor so far. At this stage, the algorithm has one candidate for the nearest neighbor, but is it truly the closest? Just like in KD tree, the ball tree doesn't stop here. It needs to make sure there isn't a closer point outside the assigned leaf. We calculate the distance from the test point to the boundary of the neighboring child leaf. If this distance is smaller than the nearest neighbor found so far, we must check the neighboring leaf as well. Otherwise, we prune that branch, ignore it, since no closer point could be inside. Ball tree partitions the space in spheres rather than rigid axes, which helps in high-dimensional spaces where distances lose meaning. Boundary-based pruning allows it to skip large parts of the dataset, making the search efficient. By using the test point's distance to the neighboring sphere's center and subtracting the radius, we can determine whether to explore further. This prevents unnecessary distance calculations, making ball tree more efficient than brute force or KD trees in many cases. Sounds great. Now that we've fully broken down K Nearest Neighbor Regressor, let's revisit and answer the key questions we left behind. Question 1. How do we find the perfect value of K? The perfect K is usually found by trial and error using cross-validation. Small k, the model follows the training data too closely and may overfit, too sensitive to noise. Large K, the model smooths out variations but may underfit, losing important patterns. So, what do we do? Try multiple values of K and pick the one with the lowest validation error. Elbow method, plot K versus error, and find the elbow where error stops decreasing significantly. Grid search, cross-validation, test multiple values and pick the one that performs best. Question 2. What happens if we pick a huge K value, like 100, if K is too large, like 100, KNN Regressor includes distant points, losing local patterns and making predictions overly smooth. KD tree and ball tree also lose efficiency since they end up comparing faraway points, making the search almost as slow as brute force. Choosing an optimal K balances accuracy and efficiency. Last question. Can we reduce dimensions and then use KD tree? Reducing dimensions might speed up KD tree, but it can distort distances. Points that were far apart in higher dimensions may become artificially close in lower dimensions, leading to incorrect nearest neighbor selection and reducing accuracy. Thank you for joining me on this exciting journey. I hope you learned something new today. If you did, don't forget to hit like and subscribe for more detective-style algorithm explorations. See you in the next one.